Hello everyone, Kirasaka is back with another video, and today we're taking a look at a classic organic chemistry reaction which is known as Hofmann rearrangement or Hofmann degradation. The reaction starts by the substrate, which is a primary amide, and this is quite an exclusive option. We shall take a look at the reasoning just in a second. Reacting with an electrophilic source of halogens, those are usually chlorine or bromine in the presence of a strong base, which is potassium hydroxide or sodium hydroxide in most cases. The intermediate that is formed in this reaction is known as an isocyanate, and it gets attacked by a nucleophile, resulting in our product. Okay, let's take a look at the reaction mechanism. Now I am drawing the primary amide, and due to basic environment, the amide gets deprotonated because it has acidic properties, and we are left with this amide anion, and it rearranges itself into a resonance, one of its resonance structures, when the negative charge now lies on the oxygen. Say we have bromine in our environment, that is the electrophilic source of halogens. It could be hypobromous acid as well, as the bromine in this case has a plus one oxidation state. Bromine Br2 would have a 0 as its oxidative charge. Okay, the double bond between oxygen and central carbon gets remade, and a substitution occurs. Bromide is liberated, and we have this monobrominated amide. One deprotonation is not enough, so the second occurs, and I am drawing now the resulting active form, the resonance structure where the negative charge lies on the oxygen, because it is the active form where the reaction takes place. And just take a look at this resonance structure. It is a pseudo-enolate because there is a double bond between the central carbon and the nitrogen, and the negative charge lies on the oxygen. Okay, so let's remake the double bond that was there before. Okay, but in this case, instead of grabbing another halogen, a rearrangement occurs. Now the electron pair that was between the substituent and the central carbon gets attached to the nitrogen, and bromide is liberated as well. And we arrive at our intermediate isocyanate. And usually in the reaction medium is made so that some nucleophiles are present in the environment, and let's just generally mark them as a nucleophile. So in this case, a nucleophile attacks this electrophilic carbon, and the electron pair between nitrogen and carbon gets now fully owned by nitrogen. Okay, so now we have this minus carbon, oxygen, and the nucleophile. And as we can imagine, somewhere the amide anion grabs a proton. So we can just mark this as an amide product. Let's say that nucleophile in this case was water. So as it attacks the electrophilic center of the isocyanate, we are now left with the intermediate, which looks like this. And as we have some hydroxide left as well, a deprotonation occurs, and now the oxygen, as it has the negative charge, makes a double bond between the central carbon and the oxygen, and CO2 gas, carbon dioxide, is liberated, and we are left just with an amine. And this only works in the case when the nucleophile is water. In other cases, when nucleophile is, for example, an alcohol, a decarboxylation would not occur because there would be a substituent here because of the additional group which is attached to the hydroxy group of an alcohol. So let's say we would have a methanol. So instead of this hydrogen, we would have a CH free group, and decarboxylation would not be feasible. Okay, so that is the reaction mechanism for Hofmann rearrangement. And to illustrate this, I have picked out a synthesis of a compound which is depicted here. This is the sodium salt of a aromatic amino carboxylic acid. And this synthesis has been done by Maki and Takeda. Okay, let's take a look at the mechanism. So we are starting with our primary amide, and I will try to shorten the mechanism now. And as the electrophilic source of halogen, now we have sodium hypochlorite, which upon hydrolysis gives sodium hydroxide and hypochlorous acid, which, by the way, is a weak acid, therefore it does not dissociate fully. Okay, as we have now our hydroxide source, the deprotonation occurs. And we are left with our amide intermediate. The electrophilic source of halogen in this case is hypochlorous acid. A double bond between central carbon and oxygen is remade, and chlorine is substituted into the amide. The deprotonation occurs once more. And this enolate type fashion intermediate, or as I would say, resonance structure, is yielded. Now the rearrangement itself occurs, and the aromatic system, the bond that was between the central carbon and the aromatic system now get attached to the nitrogen. And chloride in this step leaves as well. There we have our intermediate, the isocyanate, and as they used aqueous conditions in this step, water acts as a nucleophile towards isocyanate. a deprotonation of the carboxylic acid, which is attached to the nitrogen, occurs, and a decarboxylation as well. And as this pathway proposed, we are now left with an aromatic amine instead of the amide that we started our synthesis with.